Hey kids, ready for integration number 5? Now, integration number 5 is the last of our regular integration rules and techniques. So it's last for a reason. It's number 5 for a reason. In May, integration worksheet number 5 is way down on your worry list. Integration number 5 is broken up into 2 pieces. One piece involves a special U-substitution with logs. And the second piece is inverse trig. Yes, they are part of the curriculum. Yes, that's why you're going to practice it. Yes, why this is going to be on the Unit 6 test. No, it doesn't show up an awful lot in May. Certainly integration 1, 2, and 3 do a lot. Integration 4, some. Integration 5, very little. So certainly the reason number, so in this practice, this is nothing new. First, I am asking you to anti-differentiate. This leads into the special U-substitution with logs. And this one, I'm asking you to find the derivative of inverse trig because I'm going to give you some anti-derivative inverse trig rules. All right, so each one of these is going to lead to what we're doing. So for the first one, I'm asking you to integrate a quotient. Anytime you're trying to integrate a quotient, you want to unquotient it. How do you unquotient? Algebra, trig. For instance, 1 over secant is actually cosine, right? Unquotient. Factor, cancel, rewrite. If that doesn't work, you think U-substitution. Right, U-substitution where you break. So there was no trig, no algebra I could do here. So I rewrote this into ln x times 1 over x, and then thought, is anybody the derivative of the other? This might not be obvious to you, which is why I wanted to demonstrate this. Put ln x in a room to the first power. Right? Because if you thought of this, 1 over x is x to a power, right? X to the negative 1. And you can integrate x to the negative 1 now, but you had this ln x out here that what were you going to do with it? Wouldn't get covered up with your highlighter, right? So remember, in order for U substitution to work, you have to be able to highlight the entire integrand with u and du. So now, can you see that if I make u equal to ln x, du dx is 1 over x, so du is 1 over x dx. So when I get my highlighter out, u gets covered up, du is covered up, and the only thing that's not covered up is my power of 1. So I can substitute u to the first du, power up. Since this is an indefinite integral, I have to put u back. Nice. Now, in case you're tempted, please do not bring that 2 down. Recall, your log property, the bring it up, bring it down property, is when you have a power on x only. Ln of x squared is 2 ln x, but ln of x all squared is just ln x times ln x. There ain't nothing to be done. Right? There is no property that lets you bring down all of ln x squared. So this is your final answer. This is why this is called a special U-substitution, right? It is U-substitution. It involved logs. You were not anti-differentiating ln. Right? Did you hear that suck up? The only reason you could deal with ln being in the integrand is because its derivative was present. You don't know how to integrate just ln x. Not yet. Some people say, oh, 1 over x. No, 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 hun. The derivative of ln x is 1 over x, which is why the antiderivative of 1 over x is ln, right? Right? But when your integrand is ln x, you don't know what to do. Not yet. That's later. That takes a different integration technique that is not covered on 1 through 5. The only reason you can deal with ln x in the integrand is because its derivative is present, which is what makes U-substitution work. U-substitution only works if the derivative of U is present. Okay? So that's what we're going to spend the first part of this video on. And then the second part is practicing with inverse trig. So I've asked you to remember the derivative of inverse trig. And remember, this isn't the derivative of inverse sine of x. It's the derivative of inverse sine of U. So what is that? Remember, our inverse trig, except for inverse tangent, all had radicals. This one had nothing out front. It was 1 minus the stuff squared times the derivative of the stuff. What was our stuff? We would clean this up. We'd take the derivative of 5x squared, and we would square 5x squared. What you're going to be asked to do now is anti-differentiate that answer. Look at that answer. It's a quotient. So you have an integrand or a derivative that is a quotient. I try to unquotient it, and I try to unquotient it with algebra, trig, and U-substitution before I ever think inverse trig. But I would have tried U-substitution on this. I would have taken the derivative of 1 minus 25x to the fourth, and I would have gotten an x cubed thing. And up here, I do have x dx, but I don't have x cubed dx. I can deal with different constants, constant multiples, but I can't deal with different powers of x. U-substitution wouldn't work. So then I would think inverse trig. Duke, stop barking. There must be the wind blowing outside. My dog thinks he has to bark at it. He barks at shadows. Right, Duke? All right, so the first type. So we made a whole half of a lesson on this because we do see this kind on AP. Again, just not a lot. So recall that we used U-substitution to integrate ln x as long as we could put it into a room and suck up 1 over x. So what if I have not ln, but I have log base 2? I still have 1 over x. I still have the derivative of ln is still there, right? The derivative of ln is there. But my room to the first is an ln. But remember a log property. Log base 2 of x can be rewritten as a ratio of 2 logs, where the old argument x stays as the argument of the numerator, and then your low-hanging fruit there, 2, let it drop down and become an argument of the denominator. And then here, I'm just going to put a blank box. You can insert any base you want as long as it's the same into these boxes. Guess what base I want? Base e. So I'm going to take this expression, write 1 over x dx, write my room to the first, and then I'm going to take log base 2 of x, write it as a ratio of ln, the base I choose is e, which I write as ln, not log. But then to make my life a little simpler, ln2 is just a constant, so I'm going to osmosis that out here. It's not ln2 though, right? It's 1 over ln2. And then I have the practice problem that we did on the previous slide, right? ln x is my u. 1 over x dx is my du. So that's u to the first. To integrate that is 1 ln 2 u squared over 2 plus c. You can leave your answer this way, but in multiple choice, oh, you can't leave your answer that way. I was ahead of myself because it's an indefinite integral. So you must put the u back into the x stuff. And remember, we talked about this before. You can't bring that 2 down. Would you recognize a multiple choice answer like this as being the same as your answer? If you're writing the answer on our test or on AP's test and you write ln of x all squared divided by 1 over ln 2 and then this over 2, I mean, multiplied times, there's lots of ways you could write it, but if it's multiple choice, would you recognize this? I hope so. Now, what if I made this a definite integral? Everything would be the same for the first part, right? If I made this a definite integral, I would do all of this work. I would get here. I wouldn't have my plus c, though. Right? Because my plus c would cancel out when I did the subtraction, that the integral evaluation theorem. I can't put 1 and 2 on there because those are x numbers. But remember, u is ln of x. So what is u when x is 1? But that's 0. What is x? What is u when x is 2? ln of 2 is just ln of 2, right? So I'm going to put ln of 2, square it, and then I'm going to plug in 0. So what do I get here? This was the indefinite answer. What was the definite answer? See what I did here? ln of 2 all squared is ln 2 times ln 2. Why did I do that? Oh, bye-bye. Right? Expression in terms of x, indefinite answer, value or number, definite answer. Don't forget, somebody could use log properties on here and write this way. You don't have to. You just have to recognize it, though. Let's do one more of these. When the power on the log thing isn't a 1, it's a 3. So my room has already been created, but I've got the derivative of ln. The derivative of ln is there. So I'm going to write 1 over x dx. But my room inside the power of 3, I'm going to use my log property to rewrite log base 4 of x as ln x over ln 4. Osmosis that out. It's not just 1 over ln 4, though, is it? I mean, technically, the 1 is cubed as well. And then I have that practice problem, right? I fit a very special case. It's just that my power this time is cubed instead of to the first. So there's my u. Here's my du. Keep your constant on the outside. Integrate u cubed. Because it's an indefinite integral, put your u back. If you doubt that you've got the right answer, what can you do? Take the derivative of your red box. See that you will get this back. Now, you won't get the base 4 back, right? You'll get the ln stuff back, but then see, you'll get the divided by ln 4 cubed. All right, so we're done practicing that. So half of integration 5 worksheet has these type of problems. Now, on your antiderivative list, you need to put these formulas. They're a little bit of a dagger, mostly because of the algebra. So there's more of these, to be honest, on BC than on AB. Because remember, one of the differences between AB and BC is the level of the manipulative algebra requirements. Hey, there's only 3 formulas. That's on purpose. Okay, so while you're writing those down, actually read them right to left. I know you're writing left to right, but read them right to left. Remember, all of the integrands are derivatives, right? This is a derivative of what? Inverse sine. This is a derivative of inverse tangent. This is a derivative of inverse secant, right? Integrals are antiderivatives. The integrand is the answer to a derivative problem. Now, you're probably asking, wait, what about those ones? Well, if you remember when I taught you inverse trig derivatives, each of these, because they started with a C, were the exact same formula except negatized. So you can remember all of these, which is fine, or you can think osmosis, right? You can take the negative, osmosis it out, and then you really just have the negatives of these formulas, right? So when you're looking at an integrand that's a quotient, one of the things you can think of is, does it match inverse sine, inverse tangent, or inverse secant? You don't really have to worry about these because you can manipulate your negative out. All right, so let's do a couple of examples. This one is a definite integral. So to be honest, in May, I would not, now on unit 6 test, I might be more real, I might jump to inverse trig quicker. I hope you do too. But in May, I did not think inverse trig first. I thought U-substitution. I said to myself, no big deal. U is equal to x squared minus 1. Du dx is 2x, multiply through by the dx. Oh, I don't have any numbers in here. That's okay. 1/2 du is equal to x dx. Got out my highlighter, covered up my u, went to cover up my du. I was going to put my 1/2 on the outside, and then du is x dx. I don't have x dx. I have dx over x. That is not the same. Dagger, I would say to myself, U-substitution isn't going to work. I told you that. U-substitution only works if you can highlight everything in your integrand. Exactly. You had x times dx. You didn't have that. You had dx divided by x. Rats. Sometimes when U-substitution doesn't work, it means I just need to choose a different u. That's not what happened this time. I have a quotient. I tried to use algebra or trig to unquotient it. That didn't work. I tried to use U-substitution. That didn't work. So then I said, hey, I have a quotient with a radical in the denominator and something multiplied out front. What does that make you think of with inverse trig? Remember, the derivative of inverse secant is 1 over the square root of this x out front with absolute value, that x squared minus 1. So what do I have? I've got my 1, check. I have my division bar. I have my radical. I have the x that got squared, and I have the x out front. I know it's supposed to be absolute value, but look at the x's that I'm plugging in. They're both positive, so I don't need the absolute value. This indeed is inverse secant. So using the integral evaluation theorem, I don't know my inverse secant values as well as I know my inverse cosine values, because I had a pre-cal teacher that made me do a lot of speed trig. I had an elementary school teacher that didn't give me a calculator and made me get a common denominator to combine fractions, so I did those quickly. In May, this would be a multiple choice question. No credit for any of this work, so just as fast and as sloppy as you need to be. On the Unit 6 test, this would be worth more points than just a multiple choice, right? Because I'd have to see you got the right rule, you plugged in, you did some math and got the right answer. If you were to math, if you had a calculator in your hands, you would math 9 this, and then you would see that the decimal approximation you got was at least to 3 places past the decimal, the same as if you did pi divided by 12. Sweet. All right, let's do another one. Ooh, U-substitution. I should just use U-substitution on this, right? U is 1 minus x to the 6th. Du dx is negative 6x to the 5th. Multiply through by dx. Get my highlighter out. Cover up my u. Oh, I do have x in the numerator this time. I do have and again, I can divide, right? I have negative 1/6 over here. I have an x dx, but my powers don't match. I can't manipulate extra powers of x in here. I don't have an equation. U-substitution will not work. So I had a quotient. I tried algebra. There was no factoring of this, right? That was going to help. I tried, there's no trig that's going to help. I tried U-substitution. None of that worked. So I say to myself, well, I do have a quotient with a radical and a 1 minus. Who does that remind you of? Right? This is why you need to know your derivative rules. The derivative of inverse sine of stuff is 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. What's my stuff? Yep. Rewrite this. That way. Now, who is your u? I am going to use U-substitution, but I'm not using U-substitution where I have something into the power of 1/2. I'm using U-substitution when I have something inside of inverse sine. So U is x cubed, du dx is 3x squared. So multiply through by my dx, move that constant over, pull out your highlighter. There's your U. Here's your du, save for that constant of 1/3. So what you're going to do with that? Osmosis. Replace the x squared dx with du. 1/3 du, but the 1/3's here. So notice this time that the only things not highlighted was the inverse sine stuff. All of that was left unhighlighted. So I wasn't anti-differentiating just a power, I was anti-differentiating inverse sine. Here's my, right? This is 1 over 1 minus u squared, so that's inverse sine of u plus c. Since this is indefinite, I have to put my u back. Because I started in x, I have to end in x. My u is x cubed. Done and done. How can you check your answer? Take the derivative of this. All right, let's do another one. This is similar, but the algebra is a little bit of a dagger here, even more so. Who does this remind you of? Again, try U substitution. It's not going to work. Your du is going to be 8x dx, and you have dx over x. You can deal with the 8 by making it a 1/8 on the outside, but you can't deal with the fact that x is to the -1, not to the 1. So I have a quotient. I have a radical. I have something squared minus 1 and something out front. Who does that remind you of? The derivative of inverse secant of stuff is 1 over that. Now, I don't have absolute value, but I'm not worried about the absolute value sign not being there. Like if that was my final answer, right, when I'm taking the derivative, I would put it there. But I'm not worried, and I know this is indefinite. I'll worry about absolute value if this was definite and I was putting in a negative value. Then I would use absolute value bars. So I'm not worried about the absolute value bars missing. I'm worried about trying to match this formula because I'm super close. I have a 1 in the numerator. I have a square root minus 1. I do have something squared, but right now the x is just squared. So what can I do? And I know I have an x out here. Isn't that true? Right? Doesn't that 4x squared? Now I'm a little bothered because whatever is inside here and is before it's squared, I need to see out there. But I've only got an x. Well, this is going to be my u inside of secant, right? So if u is 2x, what's du? Just 2 dx, right? So what do I need? I really need a 2x right here, and I don't have a 2x. I just have the x, though. The x is already there. Remember, I can manipulate constants. I just have 1 dx here. Wait a second. Wait a second. Do you see what's happening here? Where's that from? Moana. I'm sorry. Look at what I've done, and this is why this algebra is a little bit of a dagger. I was worried about matching my derivative of inverse secant. Whatever is inside this squaring has to be on the outside. It's not there. I can't just put a 2 there because I want it there. But look what happens when I use U-substitution. I'm going to keep the x. I'm going to keep the radical. I'm going to keep the squared and the minus 1. What am I going to put in place of u? I'm sorry, what am I going to put in place of 2x? What am I going to put in place of 1 dx? 1 dx is the same as 1/2 du. Well, that doesn't help because look what I still have. Crap. Wait. What is u is equal to 2x? But what does that mean x is? Oh. U over 2 is equal to x. Oh. Bye-bye. And what do I have? OMG, I haven't even done any work yet. Oh crap, my battery's low. What is this now? This is inverse secant of u plus c. This is an indefinite integral. So I have to put my u back. Whoa. That was a little hairy. A lot of algebra manipulation. So this example is a triple dog dagger. I'm going to leave this example for you to try on your own, but we will do this in our live session with you. It is a dagger, but it's the calculus isn't a dagger. The algebra is a dagger. Okay, but you're in BC because your algebra is strong. All right, I will see you in our next live session.